It's good to see you all here this morning. I am going to be talking about the Kotlin programming language and what we can learn from it from decompiling its bytecode. A quick note before I get started, I do have my slides tweeted out at Gonda if you want to follow along or reference them later on. Okay, so a little bit about me. I'm a software developer at Collective Idea. We are a consulting company based in Holland, Michigan. We provide custom software solutions for our clients. Becoming a software developer was a little bit of a surprise for me. I thought I was going to be a dance teacher, so it's funny how those things work out. When I got started with programming, one of the things that interested me the most was all the different programming languages. When I was a computer science student, one of my favorite classes that I took was the programming language design and implementation. So did I enjoy programming in Snowball? Not really, but I did find it really interesting. And have I written in Null code just for fun? I most definitely have. Languages have always fascinated me, and programming languages have fascinated me in the same way. So when I found out about Kotlin, I was really excited to try it out. I didn't really have much of an idea of what to expect going into it, but I came out rather impressed. And now I would take working with Kotlin over Java any day. So what is Kotlin? It seems like a good place to start. On the website, it's described as a statically typed programming language for the JVM, Android, and the browser. So let's dig in a little bit more into what that means. It's statically typed, so we get the same type safety as we do when we're working in Java. We also can get some great autocomplete. It's statically evaluated, so that can inform the IDE about what's allowed. What makes the type system different is that the types can be inferred. We don't have to specify what type of variable is if it's clear. So in this example, we're assigning the string Victoria to name so we can leave out that it's a string. Just say val name Victoria instead of final string name equals Victoria. Null safety is also built into the type system. The nullable and non-null annotations can only get you so far in Java. With the type system built in, we always know if something could be null, and the compiler forces us to check for it. This means we run a much lower risk for null pointer exceptions. It's one thing to run something that you just wrote, get the exception, know exactly why it happened. Of course, you forgot to assign that variable. It's another when you're in uncharted territory, you're working with an outside API or some legacy code, and you're not sure where your null pointer exception's coming from. Or even worse, your user finds it. Those I could definitely live without. Some other goodies I like about Kotlin are the boilerplate reductions and the functional language features. If you haven't heard, Kotlin is much more concise than Java, but it's compact in a good way. It's not necessarily terse the way some other languages can be written, where they can be written rather unreadable, like this Perl example. You'll see lots of examples of how Kotlin can be delightfully concise. It was also developed by JetBrains, so you know you're going to have some great tooling. My primary editor these days has been Android Studio, and then there's also some really great support in IntelliJ. And then if you're an Android developer, you should be excited about the announcement at Google this past Google I/O that they're supporting Kotlin for Android. And then what's important to so many people is that it's a language for the Java virtual machine. It also targets native and JavaScript, but in this talk, we're going to be focusing on the JVM. Kotlin is completely interoperable with Java. You can pretty much seamlessly call Java from your Kotlin code and Kotlin from your Java code. It makes it really easy to use the Java libraries you're already familiar with when you're working with Kotlin. They both compile down to bytecode for the JVM to run, which brings us to the main point of this talk. Because Kotlin compiles down to bytecode, we can decompile that bytecode into Java. We can do this really easily in Android Studio or IntelliJ, and I'll show you how to do that at the end of this talk. I started out trying to decompile this bytecode kind of out of curiosity and for fun, but I discovered a lot from this, and it helped me better understand Kotlin. I also found that it also helps describe the performance and size and method count implications of using Kotlin. I was introduced to decompiling Kotlin through this blog post by Piotr about Kotlin delegation. And I was really excited about the delegation, but possibly a little bit more excited about this decompilation thing. And I'll show you his copy printer example in a little bit, but first I want to cover some other basics. So by the end of this talk, we're going to look at data classes, null safety, delegation, class extensions, and lambdas. So let's start with a simple class. This is the first kind of thing I ever tried decompiling. Let's take a user with a first name and a last name, both of them strings. Let's say the first name is non-null and immutable, so we can't change it. And the last name is mutable and nullable, so we can change it at any time, and it could be changed to null. And here's what that would look like in Kotlin. We have the class name and some properties. There's val and var, making the properties immutable and mutable, respectively. And then we have a question mark after string for last name, marking it as nullable. Already, we can see how much Kotlin does for us. It's concise with just the information that we need. So let's put the bytecode for this through the decompiler. And the result was all of this. Some things are what you might expect if you're familiar with working with Java, but let's break it down and look at each part. The first thing to notice is that the class is final by default, so we can't extend it. Limiting inheritability can make our code less burdensome to maintain in the long run. And having classes final by default could introduce a slight bit more legwork. If you do want to extend things, you just have to mark it as open, but generally it's worth it. And then we have the fields. They're private by default, which is pretty great. First name that we wanted to be immutable is marked as final. And then we have the nullable and non-null annotations. And then we have the constructor. Notice the first line of the body. Its check parameter is not null. Nullability is built into the type system, but it can only get you so far, such as if you're calling some Kotlin from Java, Java doesn't have that null safe typing system. So Kotlin does a check for us to be safe, just in these cases. And we can take a look at that method, and we can see that it explicitly points us to exactly what it is that's null, exactly what parameter, so that we can quickly find it and fix it. I often find these stack traces easier to read because we have that exact variable, find it faster, and if I have to live with nulls, this is the way that I'd want to do it. On top of that, we have our getters and our setters. So there's so much less code service we have to worry about. Notice that they reflect the mutability. There's no setter for first name. We also see that it includes the nullable and non-null annotations. You will keep seeing these everywhere. OK, that's great. But we can get even more by making it a data class. And we do that just by adding that data keyword to the beginning of the class declaration. So are you ready for this? We get all of that. We have everything that we had from before, plus some new parts. So we're just going to look at the new things. We have ordered components for each of the attributes, so component 1 for first name and component 2 for last name. These are used for destructuring class declarations. We can use that to break down a user into the different parts. This feature can be helpful in lots of different places. One example is in loops, if you're looping through a list and using all of the properties on that object. We also get a copy method, which can be really useful if you're working with immutable objects. For copy, there's also a synthetic bridge method. What we really care about with this is what it means for us. It makes it so that developers can choose if they want to modify a property when they're copying it or just make an exact copy. So that means we get all of these options for copy. Make an exact copy, change one of the attributes, change both of the attributes. We also get a toString that clearly includes all of the properties. It's very simple and helpful. And then we have hash code. How it calculates it is less interesting. That it gets it right is what I'm interested in. I don't want to have to worry about hash code. And with this, I don't have to. And then we don't have to worry about equals either. We get that for free. So we get all of that from just 4 lines of code. And those 4 lines could really be condensed down to 1. One more thing before moving on from classes is that you can declare default values. Here we're saying that if a value is not provided for first name, then you can default to use the string Victoria. And this creates a synthetic method similar to what we saw with copy. We can pair default values with named parameters as sort of a substitute for builders. Here's an example. We're clearly creating a user with just the information that we care about. We're leaving first name off, so it's going to default to Victoria. In the past, we were using Lambda for our getters and our setters and our builders, and by switching over to Kotlin, we were able to completely eliminate that dependency. Cool. So you've seen how Kotlin takes care of data class boilerplate. But what about null safety? It's one of the biggest things we hear about when people talk about Kotlin. Already we see how it checks some parameters. But what about those forced null checks? And what are our options for dealing with those? You notate that something is nullable with a question mark. So if there's a question mark, it's nullable, otherwise you're safe. It's kind of similar to Swift's optional if you're familiar with that. There's some similarities. If you don't check a nullable variable for null before you use it, it just straight up won't compile. So here, maybe string is nullable. It's marked with a question mark after string. But we're not checking for null before we call .length on it, so there's a compiler error. Because we can't compile this one, we can't decompile it. So let's look at a different example. This is the safe call operator. That's the question mark after maybe string before .length. What this does is it performs the call if it's not null and returns null otherwise. It's so much nicer than wrapping a whole bunch of things in an if not null block. So let's decompile this one. This is the result, but it doesn't exactly make sense. If maybe string had been null, this would clearly crash. When I decompiled this, I was confused for a second, but then I was reminded of the work that the compiler does for us. So let's see what happens when we really don't know that value. Will we get that null pointer exception? Let's find out. Here we're calling a method to assign a string to, or null, to maybe string, and then calling .length on it. OK, so it is adding the null check. The compiler just knew in the previous example that it could not possibly be null. We were assigning a non-null value, a string, to an immutable variable. So it knew that it couldn't possibly null, and it removed that extra check for us. If the compiler is doing this for us, imagine what other things that it's doing for us. OK. So if you really, really, really like null pointer exceptions, and you can't imagine living without them, that's the turning point if you decide to move to Kotlin or not. Don't worry, you do have options. You can use a double bank. With this, you can get around those pesky compiler errors and just call your method on that variable, whether it's not null or not, so you can get your null pointer exception. So here it is when we decompile it into Java. No doubt we'll get our null pointer exception. It explicitly does a check for null and throws that exception if it is null. A couple other null safety options. We can combine the null safe call operator with higher order functions such as let for null safe scoping. By doing so, we can pass an entire code block that's dependent on that value not being null. Here, if maybe string is not null, it is assigned to a variable it, and then we call .length to it. Otherwise, it returns null. It's a little bit unimpressive for this small example, but it's really helpful, especially when you have multi-line blocks of code. So when we decompile it, it uses a ternary to check for null. It returns the length if it's not null, and null otherwise. If we had passed in more lines to that block, it would have used an if statement instead of a ternary. And then the last null safety operator, or the null safe option that we'll look at today, is the Elvis operator. And if you turn your head on your side, you might recognize a familiar face. But with it, we can easily give an optional value if a variable is null. So it's kind of like an is not null ternary. With this, it will return the length if maybe string is not null, and 0 otherwise. So it's nice and short and sweet. And it produces the ternary we might expect. If it's not null, return the length, and 0 otherwise. Null safety and data classes are two of the biggest wins for me when it comes for Kotlin. But there's lots of other things that I like too. I mentioned delegation earlier, so let's take a look at that next. Delegation can be a good replacement for inheritance. Using composition over inheritance is one of the ways that you can get out of some of the sticky situations that you can get into with inheritance. And delegation is a form of composition. It can also cut down on some of our cognitive overhead and the number of things we have to keep track of when we're reading through and trying to understand some code. So here's the copy printer example in Kotlin. Remember, this one's not my code. It's from the blog post that I mentioned earlier in this talk. The most interesting part of this is the copy printer class declaration. It says that it copies by copy, and it prints by print right there. And then after that, we just have our interfaces for copy and for print. It's really clear and pretty simple. So let's decompile it. OK, so many more lines of code. But if we break it down, we can get a good sense of what's going on. We have the class that implements copy and print. And then we have our fields to store our copy and print objects that are called delegate0 and delegate1. Then it takes a copy and a print object into the constructor, and it assigns them to those fields. From there, it forwards the copy and the print methods to those copy and print objects that were passed in the constructor. And then finally, we just have our interfaces for copy and print, which look as you might expect. We can see all of this is nothing too crazy, but it's another example of how Kotlin reduces our buggable surface area and can improve our code reading comprehension. Okay, moving on. Something that has been really useful in Java is to have static utility classes. Some of these methods that we put into these can be pretty application specific, but some of them feel like they could just be on the class itself. For example, checking if a string is empty. It can be annoying to have to call these utility classes all the time, but Kotlin has a pretty smooth way of handling this with extensions. It allows us to access these methods directly from an instance of these objects. Extensions are a way to add functionality to a class without having to extend it or wrap it at all. And from Kotlin, it looks like we're straight up modifying a class. It sounds kind of crazy if you're coming from Java land, but it's really helpful. One place that we have found it really helpful was when we had to do a lot of math with time. We had to find a fixed set of boundaries around a time. And instead of having to call this external like datetime util class, we were able to get it directly from a datetime. So let's look at an example of extending the string class. Remember, string is final, so you can't, it can't be inherited. We'll make our own is empty. And here's what it looks like in Kotlin. It kind of straight up looks like we're modifying the class. When we declare the function name, we dot it to the class name. So here we have string.isEmpty. And because we want to be able to call it on a nullable string, we're doing string with the question mark. And then we have the body of our method. Also take quick note of the name of the file name, string.ext.kt. That'll be important for just half a second. And then when we call it, it looks like we're calling a method that has always belonged to string. This may not be unexpected from, say, like an interpreted language, but it's so different from what we're used to in Java. So let's see what's going on. OK, so it basically does the same thing as if we were to create a utility method ourselves. It creates a class. The class has the same name as that file, string.ext.kt. If we wanted to give this class a different name, there's an annotation that we could have used for that. And then it has our public static method that does as we described. Then when we call it, it calls that static method as we would with a utility class, and it passes that object in as the first parameter. In fact, this is how we would call it if we were to create our extension function in Kotlin and then use it in another bit of our Java code. I mentioned that Kotlin has a lot of functional language properties, so we should take a look at some of those. I'll admit, I'm a really big fan of functional language properties. When I first started learning how to program in Java, I was kind of upset that I couldn't pass a function into another function, and then I got really excited when I found out that you could. So let's look at an example. Let's solve a problem of creating a list of the first n squares. In Java, you'd probably have a counter and loop through and add the squares to a list, and so on until you reach n. So some looping and some conditionals. How could you do this in Kotlin? And there's this option. What this is doing is it's passing a lambda, or a code block, into the array list constructor. And it's performing that code block on each number 0 through n represented as I in the block, and then adding that as the ith element of the list. I realized that this is actually computing 0 through n minus 1, but decided to keep it this way for simplicity. You can imagine what it would look like if we were multiplying I plus 1 together instead of I. We saw a small code block being passed in for let, and that was pretty straightforward. So let's see what this one will look like. OK, a bit bigger and a bit more complex. So that we could read it a bit better, I renamed some of the variables and removed some unnecessary casting and boxing. So looking at it, it's creating a list. It's looping through the numbers and adding the square to the list and breaking when it reaches n. So it's the same concept as we might have done if we were working in Java, we might put the conditionals in a different place or use a different type of loop, but it's the same idea. But the Kotlin example was much more easier to read. We could have easily called a function in that block as well. Let's do so real quick, just so we're getting correctly the first n squares instead of 0 to n minus 1. The only thing here that changed was that call to square in that code block. And then when we decompile it, only the one line changes to call that function. The examples of functions that take lambdas that we've seen so far have all been inlined. Here's an example of the let declaration. It has the inline keyword right after public. So public inline fun, and then the rest of the signature. This means that the compiler generates the code to insert right where we call it. This is consistent with what we've seen before. So let's see how we can make one. Let's do this with a function that takes a string, prints it out, performs an operation on it, and then prints out the result. To declare that we want to pass in another function, we put the inputs of the function into parentheses, then an arrow, and then the type the function returns. And then we're also including the inline keyword in the function declaration. We print the starting value, excuse me, call the function like we would any other function, and then print the result. We see that a function takes a string and a function1 object. We can look at the interface for function1. The one corresponds to the number of parameters. And it has one method, invoke. The first thing inside the body of this method is to check to see if the parameters are null. We've seen that before. And then we're concatenating the string to print out. And then it's the interesting part. To perform the operation specified, we call function.invoke. And this is not entirely surprising since we saw the interface for function1. And then after that, we can concatenate the result to print it out again. So we have our method. Let's try calling it. There are a few ways to call it depending on what information you want to include and what practices and styles you're including in your project. But we're going to start with a more verbose example just so that we can understand all of the parts. You'll recognize some of the things from what we did before. Passing in the string hello is just like passing in any other parameter, so that's easy. The lambda is passed in curly braces. Then we have the name and the type of the variable we're passing in, an arrow, and then the operation. So let's decompile this to see what the result is. OK, so it looks like we just copied and pasted that code, which is kind of what happened. We have our start string and our concatenation to print it out. We perform the operation, and then we print out the result. Nice. So that's inline functions. They can be useful for some performance optimizations because otherwise we would have to instantiate a function object each time that it was called. A quick detour before we look at what it would be if it was not inlined. Let's see the different ways that we could have called before and after. So the first line is what we just did. Because the types can be inferred, we can leave off that type declaration, and that's the second line. If we had not specified that we wanted that variable to be called string, it would have defaulted to it. That's that third line. And then if a lambda is the last parameter to be passed into a function, it can be taken outside of the parentheses. Final thing. Let's see what it looks like when we don't have that function inlined. The only thing we're going to change is that we're going to remove that inline declaration. So here's what it looks like now. It's kind of funky. Null.instance. What is that? I do most of my investigation using command click in my editor, but that didn't work for this. For this, I had to take my shot at trying to read bytecode. And I never thought a day would come when I would try to read bytecode and actually enjoy it, but it came. And I think I figured out what was going on. So here's just a section of the bytecode. I'm not going to make you sit there and read through it. This is specifically the invoke method. But I'll show you some pseudocode with what I found. OK, so we have a class that extends Lambda and implements function 1. As we might expect, it implements invoke. And that uses a string builder to concatenate the given string with world. And then it stores the result wherever it puts return values. The other thing I saw that you might expect is a static instance to get one of these objects. And those seems to be all of the relevant parts that I saw. So why in the Java code instance was called on null? Instance was on a class that was internal to the bytecode. So when it was decompiled, it didn't have that class to reference. And the best thing that it could come up with was null. OK, so we've looked at data classes, null safety, delegation, class extensions, and lambdas. There's so many other things that you could explore using the decompiler. There's companion objects and smart casting. There's so many more collection functions. There's other control flow structures and operator overloading. And then named parameters are also pretty interesting. Before we go, I want to show you where to find the decompiler so you can keep up discovering these things on your own. Beforehand, you need to make sure you have the Kotlin plugin installed and the dependency added. This is in IntelliJ or Android Studio. And then assuming you have that set up, and a Kotlin file you want to decompile, you can go to Menu, Tools, Kotlin, Show Kotlin Bytecode, or Command-Shift-A, and just search Show Kotlin Bytecode. There you'll find a button, Decompile. And there you go. You can now continue this investigation on your own. And since I showed you how to go one way, I should probably show you how to go the other way. Android Studio offers a way for you to convert your Java code into Kotlin code. And to find that, you can go to Code, Convert Java File to Kotlin File, or Command-Shift-A and search for that. If you do nothing else when you do this, make sure to watch out for those double bangs, because those are where your null pointer exceptions are going to come from. And I'm guessing that when you're converting from Java to Kotlin, that's one of the things you're trying to eliminate. After spending quite a bit of time with Kotlin and then working with Java again, Java can seem like a long construction detour. I can still get to where I'm going, but it can be rather annoying, especially if I don't plan for it. I find that I program faster in Kotlin, and my code is much more readable. There's a lot less typing to do, less thinking to do. Interestingly enough, I feel like it's made me a better programmer in general. I've noticed that it keeps me focused on better programming practices and patterns. I can more quickly recognize when something is using, say, a map implementation. And I'm more aware of watching out for nulls. It's been really neat to see, and I encourage you to give it a try to see how it works for you. That's all I have for you today. Thank you for listening. You can find me up here after or anytime the rest of the conference, or catch me online on Twitter. Thank you for listening.